Welcome to Module 1 of Open Educational Resources submitted as a part of a group assignment to IIT Bombay by Team 1093002. I am Professor Smith from Dhansi Desai University, Nadia. These videos are released under Creative Commons Attribution 4 license. They are free to use, distribute, modify, including for commercial purpose, provided you acknowledge the source. Let's go through the learning objective of this video. That is, after going through this video, the learner should be able to understand at least what is the need of biasing. If you use transistor as an amplifier, they should also be able to identify different types of biasing and pros and cons. They should also be able to justify the use of voltage divider bias when transistor is used as an amplifier. Before going into that, first of all, see some basic of transistor in a one slide itself. That where does it operate, what is the symbol, what are the characteristics. The BJT transistor that here we are considering is an NPN transistor. So as all of you know that here the emitter, this arrow indicates the emitter current. So this is your emitter terminal, this is your collector, and this is one is your base. We have considered here an NPN transistor. If you see the output characteristic for the CE amplifier, wherein IC is and current on the y-axis and Vc is the voltage on the x-axis, we can see that you can operate this in three regions. If your operating point is somewhere here, it is basically an active region. If your operating point is somewhere here, it's nothing but saturation, and if the operating point is here, then it is nothing but your cutoff region. Now this you have to bias these two junctions in such a way that you, depending on your requirement, you can connect it in active region, saturation, or cutoff. So this table will give you some idea that the base emitter junction, base collector junction, both of them forward bias, it result into the saturation, and both reverse bias, then it's you are operating in the cutoff region. Base emitter junction forward bias and base collector junction reverse bias, then basically your operating point will lie somewhere here. And which is our requirement here? We want to bias transistor as an amplifier. But if you want to bias transistor as a switch, then you have to bias in between the saturation and cutoff. Now, from this it's somewhat clear that what is the need of biasing. Since your transistor is an active device, definitely you have to give some DC biasing, because of which its operating point can be set in any of the region as per your requirement. Setting an operating point means just setting the values of IC and VC in appropriate region. In our case, we want to use it as an amplifier. So the need here is, or requirement you can say rather, that your operating point should always be in the active region. That is confirmed. But along with that, you have to ensure that your operating point is stable against variation in beta, which is nothing but a current gain, a parameter of a transistor. Now, how come beta will change of a transistor? There are mainly two ways. That if there is change in temperature, your beta will also change. That if suppose you are operating your circuit transistor an amplifier circuit which is designed and is operating here in Bombay or at Sahara Desert, then there will be a temperature variation, and because of that there will be small change in the beta also. Similarly, beta may change even if at the same place, suppose as a person, you designer, you have designed it, after 5 years down the line, suppose that transistor is burned out and someone has replaced the transistor by the same number of the transistor, same type, but still there is no guarantee that its beta will remain same. So even though this scenario happens, our biasing should be such that your beta, even though it varies, your operating point should be stable. The first biasing that people analyzed was the base bias circuit. It is known as basically base bias circuit because your operating point is set up using the base resistor. Base resistor plays a major role in setting up IC and VC. So this is the circuit diagram. For any type of DC for biasing circuit and doing the DC analysis and determining the operating point, the simple methodology is always apply the KVL for the input loop equation, input loop, determine the input quantity in terms of IB, then shift it from input to output, where output IC, there is a relation between IB, IC equal to beta IB. Then write the output loop equation and hence determine the VC. We can see here, I will show you here that if you apply the input side from top to bottom, apply KVL. So you will get drop IB, RB, VB. So VCC drop voltage is divided into two part IB, RB and VB, where VB is nothing but this is connected to the positive, this is ground, so this is forward bias, and this is going to positive with respect to this, so definitely that will ensure, and greater, that will ensure that this junction is reverse bias. So you can see that finally you will get IB equal to VC minus VP upon RB. Similarly, go for the output loop equation, which will give you this VC. Now if you see the equation, both the equations, there is only presence of beta in one equation, that is IC. Now here what happens, that if temperature increases momentarily and if your IC increases momentarily, there is no change in the value of beta increases, so your IC will increase. But IB is being held constant here. So IC will increase, the junction temperature will increase, and if you keep on allowing this to happen, then this may lead to thermal runaway. Moreover, even if thermal runaway doesn't happen, your IC is not stable against variations of beta. The reason is because here your IB is fixed. IC is dependent on both quantity. If this increases, if somehow IB decreases, somehow we don't know how, but in that case you can hold this constant. Since IB is fixed, this biasing circuit is also known as fixed bias circuit. But this bias will make your operating point unstable, so it is seldom used as a biasing for the amplifier. So now the question that comes is operating point, how you can make it stable. As I said, if you see the equation IC equal to beta IB, if beta increases, do something that IB reduces, then IC can be. So increase in IB momentarily lead to increase in IC. So somehow some phenomena should result into decrease in IB due to this. Then operating point can be made stable. So it means that increase in IC which is an output quantity, decrease in IB which is an input quantity. That means some part of the output increase has to be carried on towards the input side. That is nothing but some sort of feedback in such a way that increase in the output quantity should result in decrease in the input quantity. So we need some sort of a negative feedback. Now if you see the diagram for the C amplifier, emitter is a common terminal. It has a presence at input and output. So let us insert a resistor at the emitter terminal and analyze it and see whether it is operating point stable or not. So this is the circuit diagram. So if you see, there is only one difference with respect to base bias, that we have included this. So applying this, so finally we will get, now if you see here IB closely, then your IB is inversely proportional to beta. So definitely that will help somehow finalize. So this equation 1 shows that your IB is inversely proportional to beta. So if your temperature increases and beta increases, there is a change in IC momentarily, but IB will also decrease, so you can have almost IC1. Logically, you can explain in this form: temperature increase, beta increase, IC increases, so the drop across this will increase. So if the drop across this increases, VB is fixed, so the voltage between base and ground will increase. If that increases, then the current IB, which is the potential difference between VCC and VB, that will decrease. Hence your IC can be held constant. So this is nothing but will make our operating point stable. So this is the circuit earlier people used. So here the operating point stability mainly depends on the design of these RE values. This is a basic prototype emitter bias circuit, but nowadays instead of using one resistor at the input side, which has to be kept very high value, it is been replaced by two different resistors, R1 and R2, as shown in the next slide. That's nothing but voltage divider bias. The reason behind it is that if you use a single resistor, you have to keep a very high value, but that will yield you your input impedance of the amplifier will reduce because it will come in parallel with the input impedance of transistor. So to have a proper input impedance AC point of view, they prefer to use a voltage divider bias, which will be further covered in the module number 2, which my team member Nisar Bhatt will cover. There are few MCQs associated with this screencast video. Go through this reasoning also. Just mail the answer to smith.ec@edu.ac.in. Your assessment result as well as the correct answer will reach you within a day or so. All this presentation has been made in online Microsoft Office website. Schematic diagram that we have drawn here, we have drawn it in student evolution version, and these are the books that we have referred to prepare this slide. Thank you very much.